Look at this fully populated 3 by 3 matrix. If you had to calculate its determinant by hand, how long would it take you? What if you had to raise it to the power of 10? You don't have to do it the hard way. In linear algebra, matrices can belong to groups called similar matrices. Despite looking different, similar matrices share identical underlying properties, like their trace, rank, and determinant. This comparison shows a standard matrix determinant on the left versus a diagonal matrix on the right. For the diagonal matrix, the zeros eliminate the need for complex cross-multiplication. To find the determinant, you simply multiply the non-zero numbers along the main diagonal. If we can systematically transform a complex matrix into a similar diagonal matrix, we bypass the heavy computation and reduce the problem to basic arithmetic. This list outlines the 5-step diagonalization procedure. Our objective is to construct two specific targets, a diagonal matrix D and a transition matrix P. Steps 1 and 2 set the foundation. You start by solving the characteristic equation to find the eigenvalues, and then calculate their corresponding eigenvectors. This flow diagram illustrates step 3, the critical test. For an n by n matrix to be diagonalizable, it must yield exactly n linearly independent eigenvectors. 3 dimensions require 3 independent eigenvectors. If your initial calculation reveals entirely distinct eigenvalues, the matrix is guaranteed to have enough independent eigenvectors. It passes the test automatically. In steps 4 and 5, we assemble matrix P by arranging the eigenvectors as columns, then construct diagonal matrix D by placing eigenvalues down the center diagonal. The sequence of eigenvectors in P must perfectly match the sequence of eigenvalues in D. Distinct eigenvalues provide a direct path to constructing matrices P and D, allowing us to successfully complete the transformation. That covers the standard scenario. But how does the procedure change if the matrix has repeated eigenvalues? A duplicate eigenvalue does not automatically prevent diagonalization, but it does mean we must verify the exact count of resulting eigenvectors. Pause and calculate the independent eigenvectors for this 2 by 2 matrix with repeated eigenvalues. It yields only 1 eigenvector. We require 2, so it fails. Without a second eigenvector to populate matrix P, this is called a defective matrix. The existence of eigenvalues is a prerequisite, but diagonalizability is only confirmed when the matrix dimension matches the total count of independent eigenvectors. We have established how to construct these components. Establishing A equals PDP inverse allows us to rapidly compute massive matrix powers. The inner matrices cancel out, collapsing the equation to A to the power of K equals P times D to the K times P inverse, raising only the diagonal entries. This eliminates the need for repetitive matrix multiplication. Following this 5-step procedure provides a systematic way to simplify complex matrices. If you have enough independent eigenvectors to construct P and D, you can transform exhaustive matrix operations into efficient arithmetic.